Okay, welcome back. We're going to pick up with part 2 of lesson 15. Okay, so what we want to talk about now is this notion of adjacency. And so what we really mean here are adjacent, we want to talk about adjacent solutions. And really what that means geometrically, if you think about a shape, we have edges on this shape if it's a polyhedron, and we want to say, well, what does it mean to be an edge? That's going to be the first notion, and then we're going to use that notion to define adjacent extreme points. Okay, so an edge, here's our definition. An edge of a polyhedron S with n decision variables is the set of solutions that are active at n minus 1 linearly independent constraints. Okay, so remember active here, satisfied. I know this is causing a lot of clicks when I write, and I apologize for that. I'm not sure. I'm trying to write quieter, and maybe that'll get better as the semester goes on. Satisfied at equality. Okay. So let's consider example 2. We have 5 constraints now, 2 non-negativities in constraints 4 and 5, and the other 3. Let's answer part A. How many linearly independent constraints need to be active for an edge of this polyhedron? Well, here again, n, the number of decision variables, is 2. So we need n minus 1 constraints to be active, i.e. 1 constraint. Right, n minus 1, it's 2 minus 1, so that's 1 constraint. Okay, and in 2 space, if 1 constraint is active, that means 1 is satisfied at equality. Of course, that would define a line in 2 space, and that's the idea here. We want to define a line in whatever space we're in. So if we want to describe the edge associated with constraint 2, what we do is, that's part B. Well, we say, okay, constraint 2 needs to be satisfied, so it's all x1, x2, such that, well, constraint 2 is this one here, and we need that satisfied at equality, so it'd be such that x1 plus x2 equals 7, right? I just turned it into an equal constraint. Alternatively, the set notation for this the edge is the set x1, x2 in S such that x1 plus x2 equals 7. And I can even draw it on its constraint 2. And if you're going to be in S, it's that red line. So it's that edge there. That's the edge. And I should note that this is all x1, x2 in S. Okay. So now we can move on to our definition. We can see that this point here, 5, 2, and this point here, 3, 4, they're on the same edge, and that's what I want. I want to say that 2 extreme points of a polyhedron S with n decision variables are adjacent if there are n minus 1 common linearly independent constraints that are active at both extreme points. In other words, 2 extreme points are adjacent if the line segment joining them is an edge of S. And you can see that's true of 3, 4, but it's not true, say, of 6, 0 and 0, 5. And indeed, that's going to be what we do in this example. Now, we can visually observe that, but we want to do this algebraically. Okay? Not just visually. Okay, so let's do that. So how do we do that? It's a bit of work here, and the work is for part A anyway, and it'll be the same for part B. Is we're just going to check all the constraints. So we want to. I'm going to go be fairly thorough here. I'm going to check first of all that these things are extreme points, and then I'm going to show that they're either adjacent or not. Okay, so for 3, 4. How do we do that? Well, I'm just going to plug it into all the constraints. Okay, so look down. I'm not going to scroll back up. I'm going to just look at the system on actually another screen. And so you should look at your paper while I'm doing this to see where I'm getting all these constraints. So constraint 1 is x1 plus 3x2 is less than or equal to 15. So I plug in 3, 4 to that. So that's x1 is 3 plus 3 times 4, that's x2. That is indeed equal to 15. So it satisfies that less than or equal to 15 at equality, so that means it's an active constraint. 2. That's x1, so that's 3, plus x2 is 4. That equals 7. That's strictly less than, that's equal to, I'm sorry, that's also active. Sorry. Okay, constraint 3. Constraint 3 is 2x1 plus x2 is less than or equal to 12. So that's 2 times 3 plus 4, which is equal to 10. That's strictly less than 12. So it satisfies that constraint. Constraint 4 is x1 is greater or equal to 0. 3 is strictly greater than 0. It satisfies that constraint. 5, well, 4 is strictly greater than 0. That's x2, remember, is greater or equal to 0 is the constraint, so this satisfies. Okay, so just let's stop there. And note that we have different definitions. So we have different definitions wrapped up in a definition of basic feasible solution. And so you can satisfy sort of different parts of that at any point in time. Right away, what I know here, just algebraically now, I mean, we knew it from the picture, but we know algebraically that this means 3, 4 is feasible. Okay. Again, to check to see whether it's also a basic solution, which would mean it's a basic feasible solution, which would mean it's an extreme point, I'll take the active constraints, form the constraint matrices, which is 1, 3, and 1, 1. Remember, and that's coming from the coefficients of constraints 1 and 2. I chose that because they are the active constraints. Okay. And I can now calculate the determinant, right, which is just 1 times 1, or 1 minus 3, which is equal to minus 2, which is not equal to 0. So I already have the solution, right? It's 3, 4. I know it's active at 2 constraints, and I know they are linearly independent. So 1 and 2 are linearly independent. The 2 active constraints are linearly independent. N equals 2 here. So that means that 3, 4 is basic. Okay, so I have basic feasible solution. So 3, 4 is a basic feasible solution. In other words, it's an extreme point. Okay. Well, I'm just going to repeat that with 5, 2. Okay, again, I'm going to check constraint 1. I see it's 5 plus 3 times 2, which is equal to 11. 15, so it satisfies it. 2, I have 5 plus 2 equals 7. That's active. 3, 2 times 5 plus 2 equals 12. Again, active. 4, 5 is strictly greater than 0. It satisfies. And 5, 2 is also greater than 0, so it satisfies. Okay, so I know what I'm talking about. So 5, 2 is feasible, right? Satisfied all the constraints. Okay, now I think about the active constraints, and I form the constraint matrix. That's going to be 1, 1 from constraint 2, and 2, 1 from constraint 3. That has a determinant of 1 minus 2, which is equal to negative 1, which is not equal to 0. So 5, 2 is basic. Note that often we say a solution is basic, or we can say it is a basic solution. That means the same thing. Okay. And then the punchline here, put in red, and I'm going to separate out so I have room, is that constraint 2 is active for both. In other words, they are adjacent. All right. Okay, so they share this common active constraint. All right, so let's do the same thing for 0, 5, and 6, 0. So in 0, 5, let's make that blue. 0, 5, again, I'm just going to go through all the constraints. So constraint 1 is 0 plus 3 times 5 equals 15, so that's active. 2, 0 plus 5, strictly less than 7, satisfies. Constraint 3 is 2 times 0 plus 5, which is less than 12, so it satisfies it. That's equal to 5. Constraint 4, 0 equals 0, obviously, so that's active. And 5 is strictly greater than 0, so that satisfies. So what does that mean? That means 0, 5 is feasible. Okay. And then I take the constraint matrix here of the active constraints, right, these fellows, 1 and 4. And that's going to be 1, 3, 1, 0. Determinant there is 0 minus 3, or minus 3, not equal to 0. So 0, 5 is basic. Okay, thus 0, 5 is a basic feasible solution, BFS for short. In other words, extreme point. Okay, so I am working with an extreme point, which of course is clear from the picture, but it's good to know. I'll repeat the same idea with 6, 0. Okay, I'm going to check all the constraints. Constraint 1, again, is 6 plus 3 times 0 equals 6, less than 15. I'll just write S for satisfied. Constraint 2 is 6 plus 0, strictly less than 7, satisfies. 3, 2 times 6 plus 0 equals 12. That's active. I'll write an A. 4, 6 strictly greater than 0. That's satisfied but not active. And 5, 0 equals 0. That's active. Okay. So I see that all the constraints are at least satisfied. Remember, active just means satisfied with equality. So 6, 0 is feasible. Okay. Let's check the determinant of the constraint matrix. For my actives, that's 5 and 3. So that's going to be 2, 1, 0, 1. That has a determinant of 2, which is not equal to 0, that's the important bit. So 6, 0 is basic. Note, I'm not concluding it's basic feasible solution there, even though I know it is because it was feasible too, because this determinant test only tells me it's basic. The checking all the constraints tells me it's feasible. So I'm re-emphasizing that. I'm being redundant with that just to really make it clear that these are different things that we're checking. Okay. Of course, the combination of those things means that I can conclude from both of those things that 6, 0 is a basic feasible solution. And in other words, we know because of theorem, 6, 0 is an extreme point. However, there are no common 0, 5 and 6, 0 have no common active constraints. Thus, they are not adjacent. Okay, we're going to stop again. And again, for the purpose of, before you go on, and for the purpose of checking the lesson test, what I'm going to ask you to do is to check to see whether the points 0, 0 and the point 3, 4 is adjacent. Okay, so that's one thing to do. Check if 0, 0 and 3, 4 are adjacent. Nope, I've done half the work for you already. So all you have to do is the work for 0, 0. The other question I'd like you to answer is how many, suppose n equaled 4, how many active and linearly independent constraints would we need? For an edge and for a basic solution. Okay. So go ahead and do that, and then you can move on to the final part of lesson